Okay, so let me continue to tell you a little bit about pattern alignment. Particularly, the pattern size is bigger than the previous case, so that primarily orientation follows the pattern on the surface. And this is just a general cartoon explaining what I'm talking about. Different regions have different orientations. And so liquid crystal director doesn't have any singular direction. Normally it has a double-ended arrows, but in order to expose the topological characteristic of the orientation of the surface, I attach only a single head. And so once again, tranquillistic energy and supplied with surface contribution, sudden splay. And in a very simplified manner, when the liquid crystal follows the orientation of the surface with a planar orientation, as I mentioned before, in order for the sudden splay contribution to survive, that Z component of director must vary over the surface. And here we start with the assumption that Z component, or in other words, previous angle remains to be constant. So in that particular case, we can just ignore sudden splay. And we also assume K11, K22, K23 to be equal to each other, which is the crudest form of approximation known as a one constant approximation. So we are talking only about the azimuthal angle variation and single constant, elastic constant. So in this case, we end up with the elastic thread density, which is just a squared gradient of phi. So the minimization is achieved by the Laplace equation of phi. So I'd like to draw a comparison between the electrostatic problem and the pattern orientation problem. You can, if you're familiar with electrostatics, electrostatic potential should satisfy the Laplace equation. The boundary condition phi is given by the surface potential distribution. So these two problems are completely parallel. If you know the solution on the one side, then you can extend to the other. So let's assume that this is a checkerboard pattern, as I mentioned at the beginning. Dark shows a vertical orientation. Bright shows a parallel orientation this way. And this is right at the surface. And the purpose of this diagram is to show how quickly this surface modulation decays. So lambda is the periodicity of the surface pattern, and this is the contrast of when the surface is just 1/10 of that periodicity. And twice that, and then half the periodicity, the variation imposed at the surface is pretty much washed away. So let's imagine that lambda is just 1 micrometer. It means if you are separated by half a micron from the surface, you will not see any variation of the azimuthal angle. but the orientation is pretty much uniform. So this is completely parallel with the surface potential problem. If you attach a positive charge, negative charge in this manner, you immediately see that the potential is just zero because you have equal number of positive and negative charges on the surface. So this orientation is just the average of the potential over the surface, and the surface details is only visible when you are very, very close to the surface. This comes from the mathematical nature of this Laplace equation, and so this is very generic. And also, the average property is the consequence of the linear property of the Laplace equation. So we split the surfaces into n different domains, having different area, SI, with different angle phi I. The average is just average of phi I with the weight of the surface. This is again completely similar to the surface potential problem. So, getting back to the original cartoon, let's assume the orientation is this way, and the surrounding yellow region dictates the orientation this way, red this way, and that way. And knowing that the liquid crystal is completely equivalent, even if you reverse the orientation. So I reversed the orientation of the blue to its 180-degree opposite, and this is also reversed. This is also reversed. So all the orientations are reversed. So these two are equivalent. And if you reverse the orientation only one domain, in this case a blue domain is orientation reversed. So you have this orientation reversed with the head is pointing downward, whereas other arrows just remain the same. Then these two orientation or patterns are not equivalent. And if you look at the liquid crystal locally inside the blue, this is perfectly equivalent to this, but globally this configuration is different from that. That generates the topological asymmetry between this situation and that situation. So once again, the total average orientation that you can achieve when the position is just a little bit away from the surface is an average of the surface orientation with the weight of area. And so in this case, you can apply that you have equal area of horizontal or parallel orientation and the same area of vertical orientation. So taking the average, what you get is 45 degrees. And you can now reverse one of the orientation. This 90-degree orientation may be reversed to minus 90 degree. Then you have 0 or plus minus 90 degree divided by 2, meaning minus 45 degree. Then you get a orientation this way. So these two are possible or average orientations that you can achieve on this particular pattern. So because locally the orientation remains the same, what is different is the topological connection across the surface, depending on the way you reverse the orientation. So these two diagonal axes give a completely equivalent, energetically equivalent states. So these two are metastable, equally stable states. So let me give you how we could create small patterns more than 10 years ago. We used an atomic force microscope to scribe the surface with tiny 1 micron squares. And these are local orientation we achieved. And two diagonal orientations are imposed. So the way this average orientation can be switched between two diagonal axes is actually the following. Let me show you this once again. By the way, this NFM technique works very nice. It gives rise to very strong anchoring. So initially, the orientation is along this diagonal axis. So we are seeing that this orientation gives a positive 45-degree twist. This one is giving a minus 45-degree twist. Because the average orientation is just in between these two. So what happens next is we apply electric field perpendicular to that average orientation. So the average orientation inside the bulk just made a 90-degree reorientation. So it made a change from this diagonal axis toward the other. And this generates 45, this is minus 45-degree twist. And on this domain, this generates 135-degree twist. And it can be proven that if you have a twist larger than 90 degrees, there is a instability of alignment. By increasing the electric field, at some point, the stability on the surface is overcome by the electric field induced torque. And there occurs a buckling of the orientation. So this is an intermediate state that you're seeing the buckling of the surface, changing the orientation abruptly from this direction with the arrow pointing this way to the opposite orientation. The arrow is pointing this way. And this is the relaxation to reduce the twist energy. So the essential part of this transition is that because we have two domains that have different topological connection, we can induce a higher twist angle that is larger than 90 degrees, and that can allow us to induce electric field-induced buckling transition. If you have just uniform orientation, you can never induce that twist, the larger twist angle more than 90 degrees, so that you can never observe electric field induced buckling transition. But the topological constraint allows for us to see this buckling. And so what is okay, so this shows transition, as I mentioned, the local non-uniformity is very much confined near the surface, just a half a micron thick layer in the case of 1 micron. Of course, if, as I mentioned, elastic property is completely scalable, and if you reduce the periodicity by factor of 2, this thickness is also reduced by a factor of 2. So it depends on how precisely you can do this business of patterning. And once you establish this orientational state, then you can apply electric field. That drives the algebraic orientation in the bulk. And that changes the orientation in the bulk that eventually induces the orientational backlink on either of the 2 types of domains. And you can extend this same idea to many different patterns, as I schematically illustrated initially. This is a schematic energy landscape, how you can construct the free energy profile of the algebraic orientation with respect to the azimuthal angle. Yellow line shows the anchoring energy for the yellow domain. This brown line is for this brown domain. And these two have a 90-degree difference. And so you have a superposition of these two. And with these 2 different orientation profiles, you have a overall profile, something like that. You can never achieve the lowest free energy because of the orientational conflict existing or induced on the surface. So the real spirit of this patterning idea is to raise the ground state energy beyond just a uniform the orientation, so that you can manipulate the landscape of the free energy to create a metastable point in many different orientation states. So the switching can take place from this 45 degree to 135 and so forth. So by superimposing this uniaxial anchoring, 90-degree phase shifted, then you can have a fold symmetrical surface. And you can induce a jumping transition from one potential well to the next. In actual experimental demonstration, you can employ in-plane electric field that can be induced by patterned electrode like this. And the processed area is sitting here. The electric field is applied along the diagonal axis. The central region was processed by atomic force microscope. And we cannot see individual domains because they are too small to see. Or in other words, we intentionally used a more numerical aperture objective lens to reject a diffracted light. And that way we can have a uniform bright state and dark state. And these bright and dark states are indefinitely stable without any biased electric voltage. So locally what's happening was exactly what I talked about. In each of the domain, the liquid crystal is undergoing a buckling transition. So these are cases we make different size domains, starting with a fairly big 8 micron by 8 micron, and down to So after about 1 micron, we became no longer be able to see the individual domains, but 2 micron, 4 micron we can see. And you can clearly see a defect line running across the processed area. These defect lines are separating 2 domains. One is oriented along this diagonal axis. The other one is oriented 90 degrees different from the other diagonal axis. And knowing that, you can now see these are defect lines or embryos of defect lines. So here is the defect line. There is the one. So this gives you more clear idea of what's happening. So these are regions where the average orientation is different because the topological connection between the partial domains are different. So now we get back to the original figure indicating that these two states, one is actually correspond to a dark state, the other one corresponds to bright state, because the domain was fairly big. We can see individual domains, but by shrinking the domain size, actually the boundary contrast tends to dominate the whole contrast. This becomes darker and darker, this becomes brighter and brighter, giving rise to the final bright and dark images. And what is really important is these dark lines here are connected with a bulk discrimination, surface discrimination line. The discrimination line is running this way and going somewhere and probably coming back right here. And the behavior of this discrimination line is really intriguing. If you apply electric field, this discrimination line, as if tension is applied, the dark line is pulled out of this region, giving way to bright boundaries. So each time the domain undergoes buckling transition, the dark defect line goes away. And finally, the whole area is consumed by bright regions. So this is just an illustration of what the buckling transition is. And by assuming a simple planar condition, you can calculate the threshold electric field by means of Gaussian flank electric contribution along with the anchoring energy. And you can just solve the equation as in the ordinary Friedrichs transition. The answer is the threshold electric field. In the case of Friedrichs transition, we talk about threshold voltage because the voltage is invariant with respect to the thickness of the cell. But in this case, electric field is what is needed to induce buckling transition. The role played by cell thickness in the case of just a particle cell is now taken over by extrapolation length, dE. So if you multiply the dE extrapolation length with the threshold electric field, you always have the constant threshold voltage. So it's an interesting comparison that cell thickness now is compared to the pattern size. And the numerical estimate is as follows, using a fairly strong anchoring energy of 10 to minus 4th power and joule per square meter. which was actually the probably strongest contact energy we can assume. The electric constant is 2 times 10 to 12 Newton, and delta epsilon is 7 times 10 to minus 11 Coulomb per meter. Then we have electric field is 5 volt per micrometer, which is fairly big, and because the display company doesn't like this value, we have to reduce, in order to make a practical device, we have to reduce this number by a factor of at least 10 or even 100 that engineers and the crystal companies are saying. And it's a good thing for us to have something to do. And, now we are trying to reduce that number by manipulating the way pattern is being created using different alignment materials, using different irradiation protocols, and all of those tuning process are contributing to reduce the switching voltage. And we have so far achieved about a factor of 10 reduction. So we're fairly close. Not exactly. So in the more fundamental side, we're trying to extend to a higher degree of multiplicity or different symmetry arrangement. This is the 6-fold symmetrical state, and these are patterns that intentionally created in a bigger scale. And again, we see as I emphasized, the contrast at the boundary is very important. And we have completely dark boundary here, and we have bright boundary, and we have neutral boundary. So there are 3 different boundary contrasts. And those different contrasts correspond to different orientation or different connection between these domains. So the transition is again involved symmetry switching. And not a simple chiral symmetry, but so to speak, this is a hyper-chiral symmetry rate because it involves 3 different states. And so these are some early examples of showing 3 different states. And the domain size was not as small as 0.25 micrometer, but so that's why we could still see individual domains. Dark, brightest, and intermediate. These are 3 different states. And by applying the electric field, we can switch different states. And so based on the average concept of calculating the average macroscopic orientation, this is the individual orientation of the individual domains. Let's say starting with 30 degree, 90 degree, 150 degree. What happens is the orientation of this domain was reversed. So 30 degree is now 210 degree. Then the average is 210 plus 90 divided by 3 makes 150 degrees. So the same is true. Now this domain has been reversed. 150 was converted to a minus 30 degree. You can take the average and you can get the average orientation in the bulk away from just half the pitch of the domain. Okay, so simple average because each of the domain has the same area. and 90, 150, 30. These are the angles. So the next question is how many multi-stability we can really practically achieve in terms of the increase of threshold for switching voltage. And the answer is we can very safely go much more beyond tri-stability, because there is a maximum bound for the voltage for switching. However large the multiplicity is, the switching voltage can never exceed the factor of 2 compared to the bistable condition. But the control of orientation of switching voltage becomes fairly involved thing, but as long as you can do that, the voltage itself remains at a fairly low level. And this is a slowly varying function of the multiplicity, and Cm is the coefficient of the ratio of the switching voltage. Okay, so we started off with that proof of concept by creating just a 100 micron by 100 micron pixel, single pixel. And of course, in order to convince industry people, we have to make something really visible by naked eye. And instead of using atomic force microscope, we started using photo alignment. And so we created a checkerboard pattern as we did, and we used primarily azo derivative molecules. Surface alignment layers was what we have been using. There are two. The biggest reason is that in order to create a checkerboard pattern, if we use cross-linking type material, we have to have a very precise positioning measurement, because that involves two-step mask processes. And on the other hand, azo alignment material is rewritable because azo photoisomerization of azo compound is reversible. So after processing the whole area to align the liquid crystal this way, then you can apply a mask, just exposing a half of the domains, then exposing the irradiating the exposed area with light polarized particle, then you get the final checkerboard pattern. So a single photo alignment process using a solid mask of 1 micrometer aperture. This is what we did. This is a fairly big aperture, and so you can see the process integrity is fairly good. And this is the dark domain situation. This is the intermediate, and this is the bright situation. And different contrast comes from the little bit misalignment of polarizer and analyzer. And this is an intermediate state. So you can just go in the complete cyclic manner from a dark state and bright state, passing through this intermediate situation. Like I said, those dark domains are boundaries between two different topological connections of the domains, and they are connected with the macroscopic discrimination lines. By reducing the size of the domain, you are no longer able to see individual domains, and you see a dark and bright and intermediate state. And so it's essentially first order phase transition. And nucleation takes place somewhere, and that expands and consumed. And normally nucleation occurs either side of the cell. We cannot really predict where it happens, but once that happens, that domain grows and consumes the whole area. So this is the prototype we made. It's already 5 years ago, and 4 centimeter by 4 centimeter, and the domain size is 1 to 2 micrometer. And still it contains lots of defects because of we didn't use clean room facility, but just ordinary room can create this many defects. So so far we used a really regular patterns, and on the other hand, I showed that the orientation is dominated by just an average of the surface orientation. So symmetry is in fact playing no role whatsoever. As long as the domains are small, we can just use whatever domain patterns you like, as long as the symmetry or average is giving the same number. And this is a dot in uniform area pattern. This is just a herringbone structure. This is just a line, simple line structure. And so depending on the nature of the patterns, the transition, backplane transition do take place. And this is a very robust transition. You can induce that transition. But depending on the shape or geometry of the pattern you use, there occurs a characteristic defect or transition pattern. So here in the stripe pattern, for example, depending on the characteristic anchoring variation, probably, you see a defect like somewhat like a defect is being formed. It's very reminiscent of the underlying patterns. All the same. And so this linear pattern is not really good. And this transition behavior is so defect rich. And the checkerboard works much better. And this is pretty much random polka dot pattern. And the random pattern works okay, but we now see a somewhat gradient of the contrast. And so, being random, there is no clear point where the transition takes place and dominate the whole area, but things turn almost randomly from anywhere, depending, pretty much reflecting the distribution of electric field. So this is what we get. And so pushing the design variation further, this is computer generated a random stripe patterns, very similar to sorry, the battery is dead. Yeah, so I didn't expect this to happen. So, well, let's take this up. Okay, well, I can recover fairly quickly. This is a computer-generated microphase separated pattern, which is very common in dialogue polymer. And actually, we employed a phase transition model for dialogue polymer and generated this pattern. And this is random, and using the periodic boundary condition, we can tile the bigger area, just repeating the same pattern again and again. And this is what we got. This shows a little bit of the base pattern here, and this as well shows some of the characteristics of the diagonal copolymer phase separated thing. But basically, it works really well. And these are the transitional state between dark state and bright state. And these are different lines that are being connected to somewhere macroscopic domain boundaries. So instead of just applying this stable device concept to a practical display or whatever devices, I believe studying the behavior of phase transition associated with discrimination should be very interesting. And you see these are the defect lines that are connected to the dark region. And if you look at things carefully inside, you can trace how the defect line is being connected inside. And depending on the buckling, these defect lines undergo very complicated behaviors. And there are many other device characteristics that we can show you, but this is a little bit different type of experiment we did. And this is the anchoring behavior as a function of temperature near the phase transition to the isotropic phase. Anchoring energy decreases fairly rapidly, similar to the scalar order parameter. So what we did is that locally heating the single spot so that the transition takes place only at the heated spot, then we can induce a local transition. So bias electric field is applied, and single point is heated by a laser spot. And each spot undergoes a buckling transition because each time the reconnection of defect line occurs, you see a periodic jumping of the defect line outside the total domain. So even though you don't see anything connecting this spot and this defect line, there must be something connecting that. And that, I believe, is the topological connection. So this, I believe, is an interesting thing. And motivated with that behavior, I started working on the surface pattern generated discrimination lines. But I'm sure my time is running out. And if you're interested, I'm very happy to show you after this session. So thank you very much for your attention.
So questions, you can actually ask questions to provoke Professor Yokoyama to continue. Okay,
First question.
One here.
yeah,
So, in the patterns that you use basically 50-50 coverage of different orientations.
Yes.
And that would make the both bistable states equivalent. I was wondering, is there some sort of transition from this bistable, well, or discontinuous transition from this equivalence of these bistable situations when you change the ratio of the areas with one orientation and the other? So that, for example, you decrease the area of the another orientation, and then at some point the system starts being bistable.
So one thing we need to stress is that the transition takes place because of the background transition in one of the domains. And background transition converts the orientation to its equivalent state. So the energy doesn't change inside the domain, irrespective of the area of that domain. So apart from the minor effect of defect lines, the majority of the energy remains the same, irrespective of the energy area ratio of the domains. So we really didn't see any difference between metastable states in terms of the depth of potential free energy.
some more questions? So